Welcome everybody to this inaugural lecture by Professor Niels Gregersen. It's a great pleasure for me to introduce Niels. My name is Lars Andersen. I'm head of department at DTU Electro. You have probably already read about Niels and what he's working with and when he was educated and all that. I will not go into that. I'll just say that one of the impressions I have gotten from Niels was when first we met in 2005 or so, maybe, when I came to the department, and Niels was a little special type, but I really have come to enjoy to work with Niels in the capacity that we work together. Meaning that you come into my office and ask for money sometime and things like that. But Niels is an extremely pleasant person. And I have also watched your transition from being a young researcher now into being a full professor and a very successful, I would say, researcher. You have both ITN grants, ERC grants, you had a Superior Outer grant, all the very prestigious grants Niels has been able to attract because of his accomplishments within nanophotonics. But also, I would really like to recommend Niels in his ability now as a professor and group leader to actually take care of his young people that are in the group and his willingness actually to lift them up, and that has also proven very successful, I would say. So that's really a good thing. Is I think we are all just waiting to hear more about single photon sources and what you are up to. So Niels, please go on.
Thank you very much, Lars, for these kind words. Is it okay? Great. Yeah, so before starting, I would simply like to remind you of the full program for today. So initially, I will do a lot of talking and we'll have the reception. And then afterwards, we have arranged for a lab tour. So if you want to, you can come and see our real experimental facility in the basement of 345. Yes, please.
I forgot one thing. We have a photographer here, and he's taking pictures that will be used on social media and in other contexts. So if you do not want to have your photograph taken and be used, please say so to Jesper, and then we will not be published anywhere. Sorry.
That's fine. Okay, so but let's get started. So there are three words here. Quantum light sources. So I guess light sources are familiar to all of us. So we all know LEDs and lasers like the one that I have in my hand, and then of course our lamp in the bedroom table. However, what does this word quantum mean? So we have a friend to assist us. So his name is Photon. So Photon is not so lucky in his love life. The dating department is not working out too well, so he's single. So a single Photon. However, even though that he's single, then he can do some amazing things that I'll get back to later on. So we generally depict him using a yellow happy face, or sometimes using a yellow arrow in the formula. A very few words about myself. So I performed my master's thesis study here at DTU together with Dan Birkedal. And then I subsequently, a little bit later, I performed my PhD studies together with Jan Sommer, who's sitting over there as a supervisor. And if you look at all this, it looks like that I spent my entire career at DTU, but this is actually not entirely true. So I spent a year and a half working in the Fabricated spin-off company, Acknowledgements Technologies. And I would say that this has given me some valuable insight into what it takes to commercialize that technology. And I'll get back to this point a little bit later. Additionally, I have visited Philadelphia many times on short stays. So I think I've spent a total of maybe 4 months working together with a group of Jean-Michel Chevard on the photonic nanowire single-photon source that I will discuss a little bit later. And then I would also like to acknowledge the people who are doing the work. So the senior staff in our group includes Luna, who is heading the theoretical activities together with me, and Batulga, who's in charge of our new experimental activity. So right now, we don't have any postdocs, but we have 6 talented PhD students: Martin, Eugene, Amanda, Claudia, Jose, and Christine, who's a shared PhD student between us and devices. Then finally, we have a student helper, Benedict. So let's now get back to our friend, the single-photon. So quantum mechanics tells us that light cannot be cut into arbitrarily small units. There's a smallest unit, which we label the photon. In classical physics, then the photon can be in box A, or it can be in box B. So this is either or. Whereas in quantum physics, then the photon can be in box A, or it can be in box B, or it can be in both box A and B at the same time. So this ability of the photon to be in 2 states at once, we refer to as superposition. So we use probability amplitude functions to describe the position of the photon. So in the top case, then we will say that the probability, which is the amplitude squared of the so-called wave function, I'll get back to those in just a while. We would say that the probability of finding the photon in box A is 0, and the probability of finding it in box B is 1. Whereas in the quantum case down here, then the probability of finding it in box A is maybe 1/2, and the finding it in box B is 1/2. Now, this story about the photon being in a superposition in 2 states at once, this might seem a little bit abstract. So to facilitate the understanding, then we can consider the morning ritual, where we start out being very much asleep and end up being wide awake. So now, as all of the coffee drinkers know, then there's a critical period between these 2 events where we are neither fully awake nor fully sleeping. So we can refer to this as a superposition between being asleep and being awake. And in terms of our probability amplitude functions, then maybe we would describe the probability of being awake as initially being 0, and then it's maybe 0.3 or something like that, and this number will depend on exactly how addicted we are to caffeine. And then we have the cup of coffee, and then we are fully awake. So let us now consider a particle in a superposition state, where it is initially either at the location A or RB. So in quantum mechanics, we describe the propagation of the quantized particle using these wave functions that are called. So they are complex oscillating mathematical wave functions. The probability of finding the particle somewhere is then given by the sum of these wave functions and then taking the amplitude square. So this image here illustrates the probability amplitude as function of position. So here, white would correspond to a very high probability, and blue would correspond to a low probability. So due to the complex nature of these wave functions, so we have oscillating phases, then there can be a modulation of the probability amplitude via, for example, constructive interference. This is when these two functions are in phase with each other, and then we have a large probability of finding the particle at that position. On the other hand, when these two are out of phase, then we have destructive interference, meaning there's a low probability of finding the particle at that position. So this stuff about wave functions and interference, that might sound a little bit complicated, but we actually witness this phenomenon in nature every day, at least if you live near the water, as I do. So if you approach the water and then you throw in a single rock, then you will observe the formation of a spherical wave away from where you drop the rock. And if you throw two rocks into the water at the same time, then you will observe these constructive and destructive interference effects where you have increased or decreased amplitudes of these outgoing waves. Of course, interference in water is not a quantum effect. So let us now consider the famous double slit experiment, which was performed approximately 100 years ago. So now we are considering not photons, but single electrons. So I guess at that time there were no single photon sources, so it was easier to generate single electrons. So this experiment now takes place by sending single electrons towards a screen with a slit. In this case, only one slit. And then the electron propagates through and further, and is detected on an observation screen. And it can hit any point on the screen. So now we conduct this experiment many times. And then we observe this intensity amplitude pattern that we see here. So we observe that the intensity pattern drops off when we go away from the center, but otherwise there's no modulation. But now let's try to perform the experiment with two slits. So again, we send in single electrons towards the screen, and they can go through these slits. And then they hit the observation screen, and we repeat this experiment many times. What we observe is this pattern, which is shown here, where you observe this distinct interference pattern. So this interference pattern cannot be explained by assuming that the electron went through slit A or slit B. The only way we can explain this interference pattern is if the single electron went through both slits at the same time. So it has been in two positions at the same time. And then there's a lot of philosophy about how to interpret this fact that the electrons apparently travel in two paths at the same time. And I would dare to say that I wouldn't think that any physicist will understand how the parts of fluid be in two places at once. We simply accept it. That's how it is. But then you can say, hey, it's completely amazing that we can have a particle which is in two places at the same time. And then you can go one step further and then say, can we actually exploit this ability for something useful? So this brings me to the outline of the rest of the presentation. So after this somewhat lengthy introduction about quantum mechanics, I will proceed to discuss what these interference phenomena and superpositions can actually be used for. Then I will proceed to discuss our own work on quantum dot single-photon sources. I will discuss their characteristics and the main challenges that we are facing in construction of these light sources. I don't have time to go through all of the stuff that we have done, but I selected one example which is close to my heart. So that is the photonic nanowire single-photon source that I will discuss a little bit later. And I will say a few words about our new experimental activity. But let's continue with these optical quantum technologies. So within this field of quantum technology, then we say that there are two quantum revolutions. So the first quantum revolution took place in the 20th century and has resulted in the semiconductor industry, which has provided us with all this amazing technology, smartphones and computers and whatnot that we have today. However, this is all classical technology in the sense that this technology does not directly exploit, for example, the superposition principle. Rather, this technology exploits consequences of quantum mechanics, so the formation of an atomic lattice and the resulting electronic band gap, which is used in the semiconductor industry. But then there's a second quantum revolution, which is now. And here we are directly, at least we are trying to directly exploit the principle of superposition to do something which is actually useful. And some of these technologies which we are seeing are quantum cryptography and ultra-sensitive sensing, and of course quantum computing. So when we talk of quantum technology, then we generally refer to these technologies down here, where we directly explore these principles of quantum mechanics. So I work at the Department of Electrical and Photonics Engineering, so I obviously work with light. So within quantum information processing, the central unit is quantum bit, or qubit, which can be in a superposition of two states as once, as the photon that we just discussed. And encoding the quantum bit on, for example, the polarization of a single photon introduces a series of advantages. So the single photon is a flying qubit, so it's compatible with optical fibers and long-distance communications, and allows us to construct a quantum network. It's also a robust qubit. Once the single photon has been emitted, then it interacts quite weakly with the environment and preserves its state. And then we can easily manipulate the single photon using off-the-shelf equipment such as beam splitters and waveguides. And finally, if we have a good source of single photons, then we can create an unlimited number of qubits. So one technology which is already out there on the market is secure communication based on quantum cryptography. So here we have Alice and Bob who want to communicate with each other without having an eavesdropper listen in on the communication. So they can do that by encoding the slipstream on single photons and by exploiting the laws of quantum mechanics in such a way that undetected eavesdropping is impossible. So this does not prevent breach of service. So Eve can always cut the fiber. but she cannot listen in on the communication without a red line lighting up with Alice and Bob. And actually, a few weeks ago, we had a demonstration of secure communication links based on quantum cryptography and single photons. So the link was between the Niels Gregersen Institute and DTU, and the work was carried out by the people in the Optical group. However, the most famous quantum technology is undoubtedly the quantum computer. So here we say that there's a race going on between two types of computers: the classical computer that we all know, and the quantum computer, which can perform certain tasks which are intractable on a classical computer. However, right now, the performance of the quantum computer is somewhat like that of a transistor. To understand the limitation, then we can consider the optical quantum computer as consisting of two parts. So we have an engine or a power supply in the form of a single photon source, which delivers the single photons which are used to encode the quantum bits of the quantum computer. And then we have a black box consisting of everything else. And the big problem that we have is that our engine is completely underpowered, and it's like that of a tracker. This slide here shows an early demonstration of something called Schur's algorithm. So Schur's algorithm is a quantum algorithm which takes advantage of superposition and interference and allows to very efficiently factorize very large numbers. So I'll not go through all of the details, but simply say that the calculation takes place by sending in single indistinguishable photons, these four guys here, into a linear network. The photons then interfere with each other, and the result is measured at the other end by single photon detectors, which are not included in this figure, revealing the result of the calculation. So in this science paper, it was demonstrated that 15 is the product of 3 and 5. And the main limitation preventing the factorization of larger numbers was the very low generation efficiency of the spontaneous parametric down conversion SPDC scheme, which was used here to generate the single photons. So this was, of course, in 2009. Since then, there has been progress. So in 2009, the group of Chaoyang Liu demonstrated something called boson sampling with 20 photons. Boson sampling is not exactly the same as Schur's algorithm, but the scaling considerations are the same. So we go from 4 photons here to 20 photons in 2019. And the main reason for this progress was the introduction of the semiconductor quantum dot, which is illustrated here, which allows for deterministic emission of single photons. I'll get back to how it works in just a moment. So this semiconductor quantum dot is really the star of the show within single photon generation. Yeah, so this brings me to our work on generating quantum light. I should say that there's also a huge activity on generating quantum light in the Acknowledgements group at DTU Electro. However, they use a different continuous variable scheme. So I will simply talk about what we do with quantum dots. So what is a single photon source? Well, we can think about it as a photon gun. When we press the trigger, then exactly one happy phase is emitted into some kind of optical aperture. The ideal single photon source should be deterministic, it should only emit a single photon at the time, which should be quantum mechanically indistinguishable. And the photon should be detected with near unity efficiency, where we define the efficiency as the number of photons detected by the collection optics per trigger. So these are also the figures of merit of the single photon source. So the first figure of merit is the purity, and I'll not talk more about that. Second figure of merit is this efficiency, which is a number between 0 and 1. And then there's also this indistinguishability, which is also a number between 0 and 1, which should be as close to 1 as possible. So my favorite objects for generating single photons are these indium arsenide quantum dots illustrated in this image here. So they can be considered as two-level systems. They consist of an island of a semiconductor material with a smaller bandgap than the surrounding material. So this full 3D confinement leads to discretized energy similar to what we have in atoms, hence the nickname artificial atom. So by using an electrical or optical excitation, we can generate excited states. And as these decay in a radiative cascade, we can, using spectral filtering of the excitonic line, obtain deterministic emission of single photons. So this is a fast and stable and efficient way of generating single photons. So these indium arsenide quantum dots feature an internal quantum efficiency of almost unity. That's very good. However, the big challenge in single photon source engineering is what happens to the photons after they have been emitted. For quantum dots in a bulk material, as illustrated here, the symmetry of the system leads to light emission in all directions. Most of the light is lost, and the efficiency is only a few percent. And some people have felt that the term zero photon source was more appropriate. So if we want to construct a single photon source with near unity efficiency, we have to control the light emission. And this can be done by placing our quantum dot inside some kind of microstructure which directs the light towards the collision axis. So this basically comes down to constructing an optical antenna with the purpose of increasing the efficiency towards unity. So many of us in this room are probably old enough to remember these Yaki-Uda type of metal antennas that we had on our rooftops in order to be able to receive TV and radio signals. For the younger generation, I need to include this picture also. So at this stage, I typically ask my students, okay, we say we want to construct an optical antenna. However, within electrical engineering, we have decades of experience with constructing very good antennas in the radio frequency machine. So what is the challenge of constructing an optical antenna? So today I will simply give you the answer. It's in these two bullet points here. So in order to avoid thermal excitation of the one photon bulk state, then we need an energy separation between the zero photon state and the one photon state, which is significantly larger than the thermal energy at room temperature, which is around 6 terahash. So this means that quantum optics experiments are generally taking place in the optical frequencies or in the near infrared machine. Unfortunately, the extinction coefficient of metals at optical frequencies is quite small. So where metals can be considered as perfect conductors in the radio frequency machine, then at optical frequencies, light penetrates significantly into the metals. And as everyone in the plasmonic community knows, then this leads to losses and a reduction of the efficiency. So these losses are really a major headache in the engineering of these devices. And while I'm not ruling out that someone could come up with a good plasmonic design for single-photon source, then people like me have been investigating alternative strategies which do not involve metals in the engineering of single-photon sources in order to avoid this loss, not saying high efficiency. Yeah, so in order to analyze and optimize these single-photon sources, then we describe the efficiency with two parameters. One is this spontaneous emission beta factor, which is the relative amount of light coupled to the optical mode of interest from the quantum dot straight here in this red sphere. And then we have a second parameter, which is the transmission of the collection efficiency gamma, which is the power detected by the lens relative to the power in this optical mode of interest. So in this picture, the efficiency is simply given by the product of theta and gamma. And our work consists of optimizing these two parameters towards unity for various different structures. However, there's also a more fundamental limitation, and that is that quantum dots, they tend to interact with the solid state environment. Unlike atoms, quantum dots interact with quantized lattice vibrations, photons we call them, in the solid state of the environment, leading to photon-induced decoherence. So this spectrum here shows a calculation of the emission from a quantum dot in a bulk material. So we observe this zero photon line, which corresponds to pure photon emission. But then we have this broad photon sideband, which corresponds to photon-assisted emission. So these the photons emitted in this photon sideband are distinguishable, and they constitute around 10% of the emission. And these photons cannot be used for optical quantum information processing. So this we need to take into account as well. So this slide shows state-of-the-art within single-photon generation. So the most successful single-photon source designs right now are the micropillar device and the open cavity geometry. Now, the success probability of the multi-photon interference experiments that we saw before scales as the product of the efficiency and the distinguishability to the power of the number of photons involved in the experiment. To get an idea of the device requirements, we can then fix an acceptable success probability, in this case 10 to the power of -7, and we can then estimate the number of photons available in the experiment as function of the efficiency and the distinguishability. So this figure down to the right here shows the number of photons or qubits available as function of the product of epsilon and eta. And we observe that if we want to work with hundreds of thousands of photons, then we have a long way to go. We can now imagine a dream device with 0.99 efficiency and distinguishability. Such a dream device would allow us to work with 800 photons and bring us deep into the machine of quantum resolution. So I'm now basically, and this is what is guiding our research, I'm asking the question, what does it take to construct such a dream device? Is this merely a question of optimization of the existing designs, or is there new research to be performed? So I will now proceed to discuss the photonic nanowire single-photon source. So these are not recent results, but on the other hand, they paved the way for some of the most advanced designs that we're looking at right now, such as the hourglass geometry. And I will say a few words about our new experiments. So the photonic nanowire single-photon source geometry is illustrated here. It consists of an indium arsenide quantum dot inside a gallium arsenide with a cylinder on top of a substrate. So here, single photons are emitted by this indium arsenide quantum dot. And by choosing the correct diameter, they will couple to the waveguide with almost 100% probability. To control the light emission and ensure good coupling to the connection objects, then two additional features must be ensured. So due to the symmetry of the system, then half of the photons propagate forward, but the other half of the photons propagate downwards, and it's necessary to implement some kind of mirror reflecting light back towards the top. Furthermore, it's necessary to implement some kind of tapering strategy, as I'll explain in the following. So this image here illustrates the field for the truncated nanowire. This is maybe a little bit difficult to see on this projector screen, but light is strongly scattered in all directions, and we observe a distinct interference pattern due to significant reflection at the semiconductor area interface. Now, our strategy for improving the far-field emission pattern is based on an adiabatic expansion of the fundamental loop. The idea here is to replace the truncated nanowire with a conical taper. So an early version of a fabricated conical taper is illustrated in this picture here. So at the taper base, the nanowire diameter is such that it supports a fundamental guided loop. As the nanowire diameter decreases, then initially the load waste decreases, but at some point the nanowire diameter becomes too small to support a fundamental load, and then the load waste rapidly expands. So this means that if we implement a very gradual reduction of the nanowire radius, then we will obtain an adiabatic expansion of the fundamental load, resulting in a narrow far-field emission pattern strongly directed towards the connection objects. So this figure over here illustrates a calculation of the transmission to the length as function of the opening angle of the tip for two numerical apertures, 2.5 and 2.8. For large opening angles, the transition is not adiabatic and the transmission is low. However, we observe that as we decrease the tip angle, then the transmission increases. And for an opening angle of 5 degrees, we obtain a 0.85 coupling for 0.8 numerical aperture of length. In 2009, my French collaborator Julien Clédon fabricated the full photonic nanowire single-photon source, including a bottom metal mirror and a top conical tapering. So the fabricated device is illustrated here. The measured efficiency was 72%, combined with a very clean single-photon emission with a D2 of 0.008. This was a world record at the time, and the story was told on the cover of Nature Photonics. So this image shows the field profile for the device, and we observed the distinct interference pattern due to reflection at the bottom of the mirror. And then we observe this nice adiabatic expansion of the fundamental load as it propagates forward. So since then, we have been working with implementing quantum dots in various micro and nanostructures, some of which are illustrated in this slide. So we're using cavity quantum electrodynamics effects to control the light emission in the micropillar structure. And we're using dielectric screening effects to control the emission in these needle nanowires. So here I would like to point out that this is 200 nanometers, the width of this nanowire. So this is 500 times smaller than the thickness of a human hair. So this means that we cannot see the structures, not even with optical microscopy, meaning that we have to rely on these scanning electron micrographs. So this is why all of these pictures are great, because they are scanning electron micrographs. I will not go into all of the figures of merits for these various structures. I'll simply say that this needle and this bullseye and this micropillar, then they all broke the world records in efficiency and at the time of publication. So this was 2010, as we discussed before. I see I didn't write the year here, so it was 2016 for the micropillar, and this was 2019. We are also presently working on this hourglass design shown here, and this rich wavelet. Unfortunately, all of these 7 images, they were not measured at DTU. And this was because that our contribution in these works was to perform optical simulations and provide design guidelines to international experimental collaborators in Germany, France, and in China, who fabricated and characterized the devices. But this is about to change, because in 2019 we received a lot of funding, and this allowed us to launch our own experimental activity. So Bazooka has been extremely busy in the past year and a half building up a full quantum optics laboratory from scratch. And it's centered around this closed cycle cryostat, which allowed us to cool our devices to very low temperatures, such that we at least partially avoid these phonon effects that we discussed earlier on. So I'll not say so much more about the equipment in the lab, because those of you who want to can come and see the lab later today. One thing I would like to point out is this quantum dot imaging setup that we have here. So a challenge for us is that when these quantum dots, they are fabricated at room, as we say, then we do not have control over their position. So they are randomly distributed on the semiconductor wafers. So this means that we need an imaging system which allows us to visualize the positions of the quantum dots. So in this image, we observe these quantum dots as white spots here, which we can localize, where we can identify the positions relative to adjacent lesser markers, and then we can subsequently construct our structures around these positions. So very quickly, a few initial nanofabrication results. So Bazooka has etched initial micropillar devices, so some of them are illustrated here. The devices are not yet perfect, and particularly suffer from the fact that the devices contain several quantum dots, because we are working with a high density quantum dots. And so here is shown the emission spectrum, and you observe several lines in the emission spectrum, even at low powers, and we attribute that to the presence of several quantum dots coupled to the chemical in these standards. However, we are receiving new wafer material with low density quantum dots, and I think if it has not already arrived, it will arrive hopefully very soon. Yes, so that brings me to the end. I'll say a few words about the future. So from the various discussions and what you read in the newspapers, then it might seem like, so I should say there's a lot of hype in this quantum technology. And if you look at the field from outside, read the newspapers, then it might seem like that the quantum computer is right around the corner. And it's definitely not. So this is also the reason why I myself am not involved myself in various spin-out companies or commercialization activities, even though I actually have a patent on photonic nanowire for the single-photon cells. Right now, we are in the scientific community facing the challenge that we have to match the maturity or lack of maturity of the technology with the expectations that we have from the industry. So this is a challenge for us. But the quantum computer is surely coming. And let's say now that we have a full-blown operational quantum computer, what can we actually do with it? I don't think anyone understands everything that the quantum computer can be used for, but we do know a few specific applications. So the National Security Agency became very interested in quantum computers when they learned that you can use this short algorithm to very efficiently crack RSA-based encryption that we're using today to encrypt our data. So this means that with the quantum computer, you can basically listen in all of the secret communication that we have today. While this has certainly been a major driver for the development of the quantum computer, I'm personally more interested in its applications in life science. So here, the pharmaceutical industry is facing the challenge that classical computers are very unsuitable for solving problems within quantum chemistry. And this leads to very time-consuming, expensive trial and error studies. However, if we had a quantum computer, then it would be very suitable by its nature to solve these problems within quantum chemistry. And one could imagine that if we had it today, then it could have been a key tool in developing a vaccine for this coronavirus, which was spreading the world for the past few years. For students and anyone else who's interested in learning more, so when we are in a transition from our old webpage, which is right now operational, to a new webpage, which is not yet operational. So right now, you should probably click here, but in a month or so, you will this one. And then, of course, we are offering all sorts of student projects, master, bachelor, of projects within theory and design, which we have been doing for years, of course, but now we are also able to offer experimental projects within fabrication and characterization of these devices. And then, of course, we are teaching the quantum optics course and teaching it together with Luca, Alexander, with this. Yes, so finally, I would like to acknowledge, of course, the funding sources. And then I would like to thank my colleagues in the group and at the department and all over DTU for making DTU such a very nice place to be and to work in. So it's really been a pleasure for me to be here for the past 20 years. And then I would like to thank my family and friends for their continuous support over the years. And then finally, I would like to thank all of you guys for your support by being with us. Thank you.